Let's pull this back up. I use a ClassLink app, and it makes Schoology so much easier to use. So Maddie says that the ClassLink app, so there is an app for ClassLink, not just the website, right? Okay, so she says that there's an app, and it makes Schoology a lot easier. Okay. Yeah, you can only log in through ClassLink, but I guess there's an app through ClassLink, so that makes it a little bit easier to get to Schoology from your phone. So maybe you should download that. I'll look into that, and I'll post some information about that later. Thanks, Maddie. Appreciate it. Okay, so here's how I want to do this. Label the top first page, 1.4 homework. 1.4 homework. When you see a green number, you're going to write the number down, and you're going to answer the question. You're not going to write the question unless you absolutely want to. Don't write the question, just write the answer. Okay. If you haven't figured this out for me yet, I do mostly completion grades for daily grades, which means all I do is I count up how many questions you do out of the total number of questions there are. There are going to be 14 for this one. If you write the number, circle it, make it big so that I can see it, I count 1, 2, 14. They're all 14 there, boom, 100. Okay, if you actually did it and follow the directions. If I can't find it and I only count 12 because you didn't label the other two, sorry. Okay, so make it easy on yourself to get easy 100s in this class. All right, so label it and just answer the question. The other directions are for those of you guys at home. So before we start, here's what I want to do. I want to really quick recap last week. And this will be helpful if you haven't done your quiz yet, because these are some questions that are on your quiz. So can you guys see that? I have a pretty basic graph here. What are the dots on the graph called? Vertices, vertexes, singular, good. What are the lines on the graph called? Edges. And if I were to put numbers on these edges, now what kind of graph is this? Weighted graph, good. If I were to use every single edge exactly one time, what kind of graph is that? Eulerian. And circuit, if I can start and end the same vertex. If I were to use every vertex one time, that's called a Hamiltonian. Okay, so those are the big vocabulary words that we have learned over the past 2 weeks. We're adding like a few more vocabulary words today, and I'm going to start with this with cycles. Cycles here, and I'm going to show you the definition. You don't need to copy this definition. It's there for you. I've already posted this to Schoology for you guys. It's on there. It's on your phone. If you check your Remind, you can follow along with me. You don't need to write this down, okay? Unless you absolutely want to. Cycle is a path that starts and ends at the same vertex, does not use an edge more than once. It looks pretty familiar to us so far. But graphs can contain many different types of cycles. Not to mention that we don't have to use every edge or vertex in order to create a cycle. And to practice this, this is what I want to show. I want you guys to do for number 1. So for number 1, it says copy the graph. I want you to copy this graph on your paper. So label number 1, copy this graph. It doesn't have to be perfect. You don't need to use a straight edge. Just make it like this. You don't need to draw it super small either. Make it nice and big on your paper so that when you're working on these graphs, you have some room. I know it's kind of hard to see it for those of you that are here. That's 1, that's 2, that's 3, that's 4, and that's 5. So I want you to copy the graph, and then what I want you to do is look back at the definition right here for a cycle, and I want you to highlight a cycle that you find in the graph. Again, don't worry about being right or wrong. I want you to see if you can put the definition into play. What we know a cycle is a path that starts and ends at the same vertex, doesn't use an edge more than once. Try to do that on your own graph, and then I'm going to show you a couple of examples of what it looks like, what you could use. $23, that's not bad. Good. Good. No. Did you highlight one? Good. Circle it or put arrows. Some people use arrows. Some people just make it darker, the path that they want to use. Good. I see a lot of correct answers out there, and not a single person had the same answer as somebody else did. Why? There's a lot of different answers. Here's one that I came up with. Started at 1, went to 2, went down to 3, went back to 1. That's a pretty simple cycle. Does that follow the definition? Did I start near the same vertex? Did I use an edge more than once? Correct, right? That's a cycle. Here's another cycle. I started at 2, go to 5, went to 3, went up to 4, went back to 2. That's another cycle. Okay, there's a lot of different cycles, and I don't even think that anybody in here had either of those two answers right there. Did anybody? No, but you guys had a lot of other different correct answers. So there's a lot of different cycles in graphs, and this is just a kind of an intro to that because I want to get to something that's a little bit more complicated towards the end of this class. So here's what I want you to do. This is what I like doing, is helping you guys take notes for yourself to help you remember. Okay, there are some times where you're going to want to explain in detail something because an open response question requires you to do that. When you're explaining something, yes, do that. Be detailed and thorough as possible. When you're taking notes on a homework assignment, you write it as easy as possible because you want to remember it. I want you, in your own words, in as few words as possible, write down for number 2 what you're going to put is a cycle to help you remember what a cycle is. Okay? Cycle starts and ends at the same vertex, doesn't use an edge more than once. That's a lot to remember. What's the easiest way to remember this? You can write whatever you want for number 2. For me, when I think of a cycle, when I go back and look at something I think of I'm creating a loop in the graph, right? That's easy for me to remember. A loop in the graph is a cycle. Doesn't that make it a little bit easier? So for whatever it is that's going to help you remember, put it in as few words as possible. That's good note-taking skills, okay? That's good note-taking skills. Few words, help you remember something like that. Got it? All right. Let me talk about how we relate this to real life and how we relate this to a job. If you guys have if you're interested in getting into networking at all, every company, doesn't matter whether you're in education, school building, or a big Fortune 500 company, has an IT department. I have a problem with my computer. It's not connecting to the internet. I call an IT guy. He has to come from the main office over here to fix it. All these computers are connected to those blue Ethernet cables to the wall. There's walls. Every single classroom runs up the walls all the way to a server room. There's a big server room on that side of the school. If you've ever been in there, the server literally goes from the ground to the ceiling, and there's hundreds and hundreds of those blue cables that are all plugged into it. And that's how we all connect to the internet. This is kind of like a really basic model of what an internet looks like, right? Internet's here in the middle, and then you have computers connected to it. Notice how some computers are connected directly to the internet, right? Some computers are connected to other computers that are connected directly to the internet, okay? That's how internet networks work. Is this red connection necessary? No. Why not? It's already connected to one of these computers. Put that as your answer for number 3. There's your number 3. Okay. What's your name over there? What's your name again? Angel, answer that question for you guys. That's why you gotta stay in school, dude. You're too good at it. But let's see if anybody can come up with a answer that relates to what we've been doing, what we just learned. We know Angel's right. It's already connected to the internet through another computer. But what made this connection unnecessary? The fact that what now exists in this network? What is this loop called? Cycle. Okay, so the cycle is in that network. That made this unnecessary. That made this graph inefficient. Think of it this way. Have any of you guys ever helped your parents put up Christmas lights during Christmas? Okay, you take the first strand, you get a little extension cord, you plug it directly into the wall, right? You put the strand up, you get the next strand, you plug it into the last strand, and you keep going. And you get to the next strand, you go all the way around the house. When you get done and you come back around, does that last strand have to also be connected to the wall? No, it doesn't need to be because it's already connected to all the way around to where the original strand was plugged into the wall. Okay, that's how Christmas lights work. That's how networks work. It would be inefficient and a waste of my money to buy another extension cord to plug the end into the wall, right? I don't need to do that. I need to save my money. This is obviously a much larger scale of that, but I don't need to waste money creating this infrastructure, this network, when it's already connected, okay? So I'm going to answer this question right away for number 4 because I want to dive right into it. How do we know that when a network is inefficient? When it has cycles, okay? And I will put something like this. Cycles equals inefficient. Did I spell that? Cycles are inefficient. I spelled that wrong too. Still spelled that wrong. I spelled it right the first time. Cycles are inefficient. In networks, in any type of networking, cycles are bad. Okay, we don't need a cycle because it's a waste of time, resources, money, whatever. Whether you're real life or whether we're doing these basic graphs here up on the screen. Okay, cycles are inefficient. Keep that little phrase in there. I would just write that down for number 4. That right there would be the thing you want to remember. Okay, cycles are inefficient for networks. So how do we relate these back to what we did last week before we move on? There's one particular thing. That Eulerian circuits, Hamiltonian circuits, and cycles are all exactly the same. How are they all exactly the same? They all do one thing exactly the same. They all start and end at the same vertex. Yeah. They all start and end at the same vertex. Okay. That's how they're all similar. They're very similar in that way. It doesn't matter. They're different. They're all different things, and we'll talk about that in a second, but they all start and end at the same vertex. Definitely want to remember that. And those of you guys at home that are watching right now, if you want to chime in, just unmute yourself. You can keep yourself unmuted, and you can answer the questions too and play along. That'd be cool. Okay. So how are they different? Number 6, how are they different? Specifically, how are cycles different than the other two? We already know the definition of Eulerian. You guys told me this at the beginning of class. Eulerian uses every edge. Hamiltonian uses every vertex. Cycles, how are they different? Anybody at home? Go back to the graph you drew in number 1. Did you use every edge or vertex? No? Does Eulerian have to use every edge? Yeah. Hamiltonian has to use every vertex? Yeah. So that's how they're different. Cycles don't have to use every edge or vertex. Okay. Cycles don't have to use every edge or vertex. So I'm not using this new term to trick you guys. It's just another vocabulary word that you want to make sure that you know the difference from. Okay, you want to make sure that you know the difference on this particular vocabulary word. You don't have to use every edge or vertex. Okay. So we have a name for this. You don't need to write this down. We have a name for these graphs. Graphs without cycles are called trees. And I'm going to show you 3 different examples, and you can kind of see why they're called trees. Because they look like tree branches. Okay. Remember, I know some of you have a hard time with some of the vocabulary here, but trees don't have cycles. There's no way for me to start at one vertex, go to another vertex, use edges more than once, and come back to this vertex. I can't do it. There's just nowhere for me to go to come back around. If there was, then it's not a tree because it has cycles. But trees don't have cycles, and that's what we call them. So I'm going to have one more little activity here before we get to a little bit bigger one. But here's what I want you guys to do with number 7. Don't draw this graph. I want you guys to draw the blank graph. So draw the blank graph on your paper with these 7 vertices. It's hard to see. If you have it on your phone, it might be a little bit easier. A, B, C, D, E, F, and G. Draw those 7 vertices, and I want you to redraw this graph without any cycles. So you're going to have to take edges away. Okay, you can only redraw edges that already exist. So for example, you can connect A and B because there is a connection between A and B already, but you cannot connect B and E. Don't do that because there's not one connection there. All right. There's a lot of different answers to this. So redraw without any cycles. Okay, redraw it without any cycles. See if you can redraw it without any cycles. There's so many different answers. Let's see what we got. Good. 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 Now take one out. Scratch one out. Now you have a cycle, right? Because you looped around. So scratch one of those out. Yeah. There you go. Now. Good. Good. Take one out. You created a cycle. Now you don't have a cycle anymore, right? Okay. All right. Now I want you to do this, and I forgot to do this in my other classes, but good, this is the one I'm recording. Count 1, 2, 3, 4, 5, 6, 7. There's 7 vertices, right? Count how many edges you used in the graph you just drew. Count how many edges you just used. How many is it? 6. Do you think that's always going to be the case every single time? If you don't have a cycle in a graph, the edges are going to be one less. Look at the 2 that I came up with. Here's an example of one. No cycles. 1, 2, 3, 4, 5, 6. Here's another example. 1, 2, 3, 4, 5, 6. You think that's always going to be the case this time? It is. Yeah. If you have a graph that has no cycles, the number of edges is always going to be one less than the number of vertices. And it's just another way to check your work. Okay. It's just another way to check. And no cycles. This is a tree, but it's called a spanning tree because we created it from an existing graph. Okay. We deleted edges. We removed edges. So it's still a tree nonetheless, but we added that word spanning tree in there. Okay. How are you guys doing at home? You good? Give me a thumbs up if you're doing all right. Cool. Okay. Moving on. Answer this real quick. Can graphs have multiple spanning trees? Yes or no? We just proved this. I don't think a single one of you guys had the same graph as I walked around. Yes or no, can they have multiple spanning trees? Yeah, absolutely. There's going to be so many different combinations of the way you could have connected those. That's where that spanning tree comes in there. As we work some of these answers, you're going to see there's multiple different ways to do something where you might come up with the same answer towards at the end. Okay. So here's an activity. I don't want to take too long. I want to see if you guys can figure this out. This is kind of like the traveling salesperson problem. And I'm going to read this and I'm going to show you where to start. This is going to be number 9. If you don't have a lot of room on the bottom of your paper, then switch to the next page because you need at least like a third of your page to draw this out. Okay. Here's what you're going to try to do. I'm not going to give you too long to figure this out because I want to show you the best way to approach a problem like this. But here's a railroad system that connects 5 cities. We're trying to build a railroad system to connect 5 cities. But we're trying to do it in the least amount of money. And this table shows how much money it costs to build a railroad between each of those cities. You don't want to create any cycles in this graph because it'll be inefficient. For example, if I have a railroad between A and C, and I have a railroad between B and A, do I need a railroad between B and C? No, I can get from B to go to A first and then to C. So I don't need to do that. So don't create cycles in your graph. But what you're trying to do is you're trying to do this in the least possible cost. I'm going to get you started out for number 9. The first thing you got to do is you got to create those 5 cities. So create 5 vertices for the 5 cities. You don't need to write city down. Just put A, B, C, D, E. Okay. Spread them out on your paper though. This works well when you spread these out. It doesn't matter where you put them. The only thing that matters is how you connect them. Okay. Doesn't matter where you put them. The only thing that matters is how you connect them. Once you write those 5 cities down, I'll go back to the last slide so you can see the numbers. Good. Okay. So just think about it. I'm gonna give you about 2 to 3 minutes, about 3 minutes. But look at the table. If you were the person that was spending the money building this railroad, which 2 cities are you going to connect first and why? Anybody at home? 2. E and A. Why? It's the cheapest one. It's literally the cheapest one. E to A is the cheapest one. Why not build that one first? I know I'm not going to create a cycle by building just one railroad. So why don't you start with that one and work from there? Okay. Yeah. It doesn't really matter the order that you put them in, though. Just how you connect them. But if you want to do it the way I did it, I just did it like that. Good. Okay. Here's the table again. I always start with that one. If you think you have an answer, and even if you have an answer at home, add up the railroads that you used, that you built, and show me what you got. And I'll tell you if you're right or wrong. If you are at home and you want me to check, send me a private chat to the one that says Coach Cisneros, not host. That's the one I'll see. And I'll tell you if you're right or wrong. See if you can come up with an answer. Can you hear me now? Okay. I just plugged it into my. I just have to carry around that portable charger. Yeah, send me a private chat if you think you have the total cost, and I'll tell you if you're right. There's one lower, Maddie. That's the second lowest way to do it, I believe, Maddie, but it's not the lowest. What'd you get? That's correct. Anybody else think they have an answer? Yeah. But you gotta add it up. Oh, that's it right there. You're off by 1. No, 100,000. Yeah. What'd you get? What was that total? It's kind of hard, right? It takes a lot of guess and check in your mind to do this. So I'm gonna show you. Don't worry if you didn't get it right. It's not. Don't worry if you didn't get it right, because what I'm going to show you here, the last thing I'm going to show you today, is I'm going to show you the best way to approach something like this. And I'm going to give you a 5-step process. And you follow these steps, you're going to know how to do this every single time and get it right every single time. Okay. If you got close to it, this is what the correct answer is: 1.8 million. So 1,800,000. Close. Is that what you got? 2.5. You're really close, Angel. And what's your name again? Gonzalo got it right. He got it a second ago. I don't know if anybody else sent me a chat. So, not the point. The point in that you didn't get it right. That's not the point here. This is what if you pay attention to. We just found a spanning tree that had the lowest possible weight. That's called a minimum spanning tree. Okay, so that's all that means, is that we found it with the minimum possible weight. If you pay attention to anything at home, here in class, pay attention to this. This next thing is what you guys are going to use for your project, your big part of your project. And let me give you a sense of relief here if you don't like projects. I do this first project for a reason, to get you guys started off on the right foot. The average grade on this project is a 90. Okay, the average grade on this project. So how many of you would love to start out with an A as a major grade average in this class? Okay, so pay attention to this so that you don't have any problems doing this project when I assign it to you guys on Thursday. All right. There's an algorithm, and you don't need to copy this down, but I guarantee you that after we do it once together, you're going to remember how to do this. Okay. So I'm going to show you the steps, and then we're going to do the steps. Step 1 is we're going to create a blank graph. We're going to duplicate every vertex that we have. That's exactly what we did first. We wrote down all those cities, right? Here's the step that some of you may have been doing in your head. I think this is what Marshall was doing. He was looking for the smallest numbers first, right? Looking for the smallest numbers. So what we're going to do is we're going to take numbers on the next example problem, and we're going to put them in order from least to greatest. Okay, that will help us figure out which numbers we want to use first. We're going to start with the smallest number, and we're going to connect that one first, and we're going to continue connecting it like that as long as it doesn't create a cycle. If it creates a cycle, we skip it and move to the next one. Okay, and we're going to take that weight off the list and keep going. We're going to repeat that until we create a tree, a spanning tree, no cycle, all of them connected, but no cycles. Okay, so here's how it's going to look. I know that if you don't have it on your phone, this might be hard to see. That's fine. I will pop up what you should, I want to point to what we're doing, and I'll pop up some things. So I made this a little bit bigger. Okay, there's 7 islands that we're going to connect with bridges. Okay, and I'm the contractor. I want to build these bridges in the least possible cost. These are the miles in between each island. The shorter the mileage, the cheaper it's going to be. Okay, I want to connect all these bridges together so that I can get from one island to another. Same thing as last time, no cycles. I may have to cross several bridges to get from one island to another. So if you can't see that, that's fine. I'll still pop up. Just follow along or pull it up on your phone. Up to you. Step 1, what do we do? All the dots, all the vertices. So let's put all the vertices. Make it easy on yourself, guys. Do 2 things as you do this on your paper. Put number 10. Go ahead and put number 10. You don't need to write out island. I did that on here just so you know what we're talking about, but just put A, B, C, D, E, F, G, like Spread it out. You might want to use about half a page for this. It's a lot easier when you spread it out on your paper and you're connecting rather than make it really small. Okay, so spread it out. This is number 10. This is number 10. And I'll give you a second to write all those vertices out. But if you follow this process here, it is going to get you the right answer every time. And you guys at home, hopefully you're following along too. All right. The next step is to put all these numbers in order from least to greatest. Okay, to save us some time, I already did it for you. You can just copy it there. Now, you do need to have these on your paper. Make sure to copy these in order from least to greatest because you'll want these on your paper to go through them. I like to write them vertically like that, where I go start at the top and down on the side of my page. Some of you like to write it like this, 3, 4, 5, 6, 6, and so on. It doesn't matter. It really doesn't matter. As long as you have them in order. As long as you have them in order, it really doesn't matter which direction you write these numbers. Now, if a number pops up multiple times, you have to write it multiple times. That makes a difference. You need to be able to use multiple of them. So give you about 20 more seconds to copy those numbers in order from least to greatest, and I'm going to show you how this works. We're going to build these bridges in the least possible number of miles. So I'm going to start with 3. I start with 3. I find 3 on the table. I know it's real small for you if you don't have it up on your phone. I noticed that 3 connects B and F. So that's the first one I'm going to use. I connect them. It's hard to see. I didn't make this dark enough. Label it 3 as well so that you can go back and add them easily. And then I cross it off the list. The first one I don't have to check for cycles. It's not going to create a cycle by itself. So obviously I can just connect that. That's my first bridge I'm going to build. That's the smallest one, 3 miles. So we're going to go to the next one. Look for the 4 on the list. I see that 4 connects B and C. B and C is not going to create a cycle, so I'll go ahead and connect that one. Label it 4. Sorry. Cross it off the list. Okay, watch this next one, but don't write anything down. Watch this next one. Look at the 5. 5 connects C and F. Do I want to connect that one? No. That immediately creates a cycle because this is an unnecessary bridge I need to build. If I want to go from F to C, I can go to B first and then get to C. So I'm not going to draw that one on there. I'm going to cross it off the list and move on to the next one. Okay? The next one is a 6, and there's 2 6s. Do you think it matters which 6 we use first? No. 6 is the same as 6. It doesn't matter which one we use. I'm just going to pick the first one that I see on the table, and it's this one right here. Okay? It was C and E, and I labeled it 6, crossed one of those 6s off the list. Then we'll see if we can use the other 6. If we can, good. Use it. If we can't, don't use it because it's and you'll see pretty quickly the other 6 is F to E. It creates a cycle. I'm not going to use that one. Okay, so I'm going to cross it off the list and move on. Now, here's where your graph might have been a little bit different than mine. You might have done the F to E first, which means you're not going to use the C to E. That's okay. You would have been your graph would have looked a little different. Your final answer would have been exactly the same. 6 is equal to 6. Same value. Okay. So we're moving on. Number 7. We have to keep going because A, G, and D are not connected yet. 7 is B to G. That one works. I still haven't created a cycle in my graph. There's no loop anywhere. So I'll connect that one, cross it off the list, start with one of the 8s. Doesn't matter which 8 we start with. I just started with the first one I see on the table. A to C. Can I connect A to C even though it crosses those other ones? Yeah, I can connect it. It doesn't This is why I like when I draw them on my paper, like when I personally do it, I make the vertices really big, okay? Because this is a vertex, but where these intersect, they're not. Remember, you could have made this not intersect if you put A down here. So it doesn't matter where you put them. The only thing that matters is how you connect them. How you connect them. I got to keep going because D isn't connected to anything yet. I look at the next 8 over, and it actually is A to D. And so now I've connected D to the other islands. I still haven't created a cycle. There's no way for me to get on one island and loop back around to that island without backtracking. It's just not possible. But what do you notice now? What's the deal with all the islands now? They're all connected. Okay? They're all together. I can get from any island to any other island if I want to using the bridge. And not only that, but I did it in the least number of miles. The least number of miles. I did it at the lowest number possible. What's the last thing I need to do? What's the last thing I should do with all these numbers? Add them up. Yeah, count them up. When I add them all up, I get 36. Okay, 36 miles. I just built, as this contractor, I just built the least possible system, bridge system, in the least possible cost and still connected everything. On a scale of 1 to 10, how hard do you think that is? It's pretty easy, right? Okay. You guys this is what you guys are gonna do on your project. There's a little bit. I'm gonna expand it a little bit more. Okay, expand it a little bit more. So before you guys get to your project, you guys are gonna have 4 practice problems. So here's the last 4 slides. Some of you might be getting ahead and seeing these. For the following 4 slides, you're gonna do exactly what we just did. You're gonna draw this tree, and you're gonna include the minimum weight. Okay, make sure you do both. So there's 11, 12, 13, and 14. So you may want to look at them on your phone. In my other classes, I did 11 with you guys. You want me to do one more with you because it's a little bit different? I'll give you one more answer. So you only have to do 3 on your own. All right, so I'm going to do number 11 for you guys at home too. So you guys can follow along. Anybody have any questions at home? Give me a thumbs up if you're good. Thanks, guys. Jayla, Kate, are y'all there? Maybe not.
Yeah, I'm good.
Okay. All right, let's do question 11. Label question 11 on your paper. What's the first thing we should do? Before that. Before that. Yeah, we got to redraw all these because you don't have them on your paper yet. So we need to do that first. We can't connect them without vertices. Here's what I like to do. I like to just, when I draw it, I try to position them in the same way that they're already positioned. So when I connect them, it's pretty easy. G, C's like right there. D, E, H. This is what we should start out with because we can't connect them if we don't have vertices. And we need to label the vertices. When I try to give you these graphs, I'm going to try to give you ones that are already all labeled so you don't do a bunch of unnecessary work on your own. Okay. Now we need to put them in order from least to greatest. Okay. When you do this, you got to be really careful that you don't forget any numbers. That's the only thing the only hard part. Don't forget any numbers. I just start with the ones and I look for how many there are and then I go from there. So how many ones are there? There's 2 ones. 1, 2. How many 2s? Just 1, right? How many 3s? I'll see that part. How many 3s? Just 1? Oh, there's 2. How many 4s? 2. 5? Just 1? 2 6s? 1 7? 8s? No. 1 9, 1 10. Okay, I think that's it. All right. So I got them in order from least to greatest. Let me grab a different color, make this a little bit easier to see. Let's start with the ones and start connecting if we can. 1 connects from F to G. Since it's the very first one, I don't need to worry about any cycles. I'll label it, connect it, label it, and cross it off the list. What about the other one, G to C? Can I connect that one? Yep. I have not created a cycle. There's no way for me to loop around. Connect it, label it, and then cross it off the list. 2, B to F. Yep. Connect it, label it, cross it off the list. 3, does it matter which one we use first? No, just pick one. The first one I see is A to F. Can I connect A to F?
Yes.
Yeah. I still have not created a cycle, but I also still have not connected every vertex. So every vertex has to be connected to in some way. The other 3 is D to E. Can I connect that one?
Yes.
Yeah. It's still not connected to everything else, but they can connect to each other. What do you notice about the 2 4s? Yeah, if you use both of them, they're going to create a cycle. Does it matter which one we use? No, pick one of them. So here's another example where your graph could look different. Your final answer is going to be the same. The final number is going to be the same. So some people pick this one. Some people pick the outside one. I just picked the H to E one. That means I can't use the other one. So I'm going to cross the other 4 off because I can't use this one. If you want to use this one and not that one, then do that. Final answer is going to be the same. The 5. Can I use the 5?
Yes.
G to D. 5 connected. Do I need to keep going? No. Don't need to keep going. I've created a tree because every vertex is connected, but there's no cycles. The final thing you need to do is you need to write on your paper the minimum weight. This is the final answer. What's the minimum weight? You're going to have to add it all up. 19. Good. So there's your final answer. 19. How do you guys feel about this? You think you can do 3 more on your own? Like that? I think so. How about you guys at home? Cool. Maddie's good.
I feel good.
Good. Glad to see you, Jayla. Glad you're here.